everyone, welcome to Diksha Vedantu YouTube channel. I hope you all are doing really great. I hope you all are enjoying life, and I really hope that the chapter we are going to start today, we are going to learn today, makes your life a little bit more interesting, a little bit more colorful. Okay, before that I have one question for you. Are you a mountain person or are you a beach person? Do you like watching sunset from a mountain or would you like watching sunset from a beach? Well, whatever it is that you like, there is one common thing in both these scenarios which lets us watch those beautiful sunrise or sunset, those pretty skies, those pretty clouds. That is exactly, it is light which lets us see those pretty objects. Now yes, it's a very important, very scoring chapter, yada yada. But it's also very wonderful, very lovely chapter which lets us study why we see objects. It lets us study why we see a reflection in the mirror. We'll study that. It also lets us see why the light plays some tricks on us when we see an object through water or when we see an object through glass, which is refraction, and hence we'll study power of a lens. So stay with me. It will be a very informative lecture for your concepts, for your theories. If you are here for revision, it's a perfect chapter for you, perfect video for you. And if you have never even heard the word light, just stay here and you will see what exactly it is, how we use it, how it plays tricks on our minds and all that. Now, yes ma'am, it will be interesting and all, but I hate those ray diagrams and those sign conventions and all. Yeah, it's fine. After this one shot, you won't say that. I promise you that. Now, let's start with a very basic question. What is light? The chapter is light, so the answer comes, what exactly is light? Light is nothing from a basic definition. It's just a form of energy that enables us to see the world around us. See those pretty skies, those pretty clouds around us. You know, you can see me because of light. Okay, I can see you because of light, but what is it made of? So here comes our very own Isaac Newton. He came and he said that light is made up of a particle that he called as corpuscles, which we now say that it's a photon and it has a speed of 3 × 10⁸ meter per second. Then Huygens come into picture. He says, hey Newton, no, this is not the perfect interpretation. Light is not a particle, it is a wave. It is actually an electromagnetic waves which do not need material medium to travel. So is it a particle now or is it a wave now? The question arises, ma'am, it's very confusing. One is saying, our very own Newton sir is saying that it's a particle, but Huygens sir comes and he says that it's a electromagnetic wave and it doesn't even need material medium to travel. What does that mean? Okay, so do you know that in our space there is no air, it's just vacuum, right? So but the light is coming from sun and here is our earth. Now there is nothing between our sun and our earth, but still the sunlight from the sun reaches us even there is no medium between them. Which means what? Which means that this light can travel without requiring any material medium. Okay, that's great. So, but the question still arises, is light a particle or is light a wave? Then we got to know about a very pretty thing about light, that it has dual nature. Just like we react to a different situation in a different manner, same light acts as a different, if once a particle, sometimes a wave in different situations, which says light acts both as a wave and a particle and it changes its behavior according to the situation. So in solar panels, when the particles of light, the light from the sunlight is coming, okay, and this is our solar panel. When the light is hitting the solar panel, what is exactly doing is ejecting the electron from the solar panel. Just remember this much now. You don't need to go into the depth. It the sunlight hits the solar panel, in that case it is acting like a particle. But when the same light, mind my language, the same sunlight, we make it pass through a prism, that light now is acting like a wave. So did you see that same light is acting as a particle and that same light is acting like a wave depending on the situation we presented in front of it. So okay, we defined that light is a form of energy. So we saw what is it made up of, what is it has particle nature or it has wave nature or it has dual nature. Now you mentioned one more thing, ma'am, that it enables us to see the world around us. How is that? How do we see objects? So how do we see objects? The answer to that is, imagine there is a light coming from the sun. It's hitting me. Okay, the light is hitting me and then it is hitting that camera which you are watching from, right? The light is hitting me and then it is bouncing back from me. What is it doing? Bouncing back from me and going into your eyes, the camera's eyes, right? Hence your eyes. The light is coming, bouncing back from me and hitting you, your eyes, and hence the light that bounced back from me is the exact light you're seeing and it is enabling you to see me. Similarly, the cloud is hitting the clouds and it then entering your eyes and hence you are able to see that light and hence you are able to see that cloud. Very good. So what is it? It is the bouncing back of light. What is it? Bouncing back of light when it strikes a surface. Now there is one thing mentioned, without being absorbed. What does this mean? Without being absorbed means that if a light is hitting me and it gets completely absorbed, then it won't reach your eyes, right? Then how will you see me? How will you study? How will you score? Right? So it needs to bounce back without getting absorbed. Okay, it needs to bounce back without getting absorbed. Okay, let's dive a bit into more physics of reflection, and that is what we are here for. So we'll study about some laws of reflection. Now, okay, what is reflection? And that is how we see objects. Now what I mentioned here is the keyword bouncing back. What does that mean? What do we exactly say the bouncing back means? It means that the light is getting reflected. Correct. Abhi kya hai? Now what I mentioned here is a keyword you should look for is the bouncing back of light. When light hits me, it bounced back. What does that bouncing back means? What do we call it? Exactly. It means reflection of light. So how do we see objects? We see objects because light reflects back from the object and it travels straight to your eyes, and that's how you see the light. Very good. Now we have seen the reflection, what light is, what it is made up of, how do we see object. Let's dive more into of it a physics perspective. So we'll study about reflection a little bit more, what are its laws, how it is being done and everything. So let's see the laws of reflection. The laws of reflection says that the angle of incidence, listen very carefully, the angle of incidence is equal to the angle of reflection. Okay, before that, what happens in reflection exactly? What did I say? Light will come and bounce back from me. So the light is coming, the light which is coming is called incident ray. This is called incident ray. Okay, it bounces on this surface. Light, can you see this? At this point it hits the surface and then goes back, correct, which is called our reflected ray. Now what we do is, the point where it is hitting that surface, we draw a normal perpendicular to that surface. This is our mirror. This is incident ray. Where it is getting incident, we draw a normal perpendicular to that surface. Correct? And then the light gets reflected back. This is a basic motto of what reflection, how reflection is being done. Now, we need to study what exactly is happening here. So what the laws of reflection says, it says that the angle of incidence is equal to the angle of reflection. So the light, the incident ray is being incident on a surface, and we drew a normal here. What we do is, we say that from the normal we have this angle here, this one. This is called angle of incidence, and then the reflected ray goes back, so this is called the angle of reflection. Very good. What the laws of reflection says is that the angle of incidence will always be equal to the angle of reflection. Very simple. Great. Now the next thing it says is the incident ray, which is this one, the incident ray, the normal to the mirror at the point of incidence. This is our point of incidence. This we drew a normal to the mirror. Understandable? The normal to the mirror at the point of incidence and the reflected ray all lie in the same plane. That means the incident ray coming and the reflected ray going back and the normal all lies in the same plane. Thus we can see all lie in this same plane. It is not happening that the incident ray comes like this and goes like this out of the plane. Let's assume this board is one 2D plane. The incident ray is coming parallel to it, but is not going outside of this board, right? It stays in that board, and similarly same for this normal here. Okay, very good. Moving on to the next thing. Now we need to study in this chapter, we need to study basically about the image formation because of this light. To start the image formation, let's start with a very basic, very simple thing, which is the image formation from a plane mirror. Now we have all used plane mirrors. You get ready looking at it in the morning, when you go to shave your beards or apply some makeup, so we all use plane mirrors for that in our houses normally. So we're going to see how that image is being formed in that plane mirror. So image formation by the plane mirror is our next topic. So what it says is, the first thing, very important, is that the size of image is equal to the size of the object. It means if I stand in front of a plane mirror and there is a plane mirror in front of me, if I stand here, it will be of exact same height as I am, right? If I'm 7 feet, it will show me of 7 feet. If I am 5 feet, it will show me of 5 feet. Okay, that is the first thing. Then the second thing it says is that the image formed is as far behind the mirror as the object. What does this mean? This means that if I placed a mirror here, the image formed will be as far from me. If my head is like say 1 meter away from the mirror, the head of the image formed behind the mirror will also be 1 meter away from the mirror. If I stand 10 meters away from the mirror, my image formed will also be 10 meters away from that mirror, that plane of mirror. Okay, which basically it means that this distance, let's say S. So this distance is same as that of this distance. Understanding? And this height, let's say H, it is same as of the height of your image. Understanding? Okay, great. Now the third point, very important, it says that the image is laterally inverted. What does laterally inverted mean, ma'am? Okay, if I am standing in a mirror, my left hand in the mirror, it will look like that I'm raising my right hand. So it switches the mirror sideways. If I wave by my right hand, it will look in the mirror that I'm waving by my left hand. That is it. That is just you mean by laterally inverted. And one more thing, the image that a plane mirror forms is virtual and direct. Now what virtual and direct means? Virtual means that imagine the rays will be going like this from this person. This is our object. Okay, the rays will be going like this and it will come back like this, let's say. Okay, so it will appear to us that the rays are coming from behind the mirror. The rays are coming, so we will see that the image is forming behind the mirror, so that image is virtual. The image is not being, the ray is reflected back, it came back, okay, but the image is not formed here. The image was formed here without the convergence of real rays. Real ray came back and its image, its illusion looked like it's making the image. That's why it's called a virtual image. Erect image just meant that your head will look, if your head is upwards, it will, in the mirror it will always be upwards and it won't invert you horizontally, okay, it won't look you, it won't show you that your head is upside down. That is great. Okay, moving on to next one. Our main topic in this actual chapter is not the study of image by plane mirror, it's actually the study of image by spherical mirrors, which is very important. And my friend, you are right now doing a very important contribution to the science, to especially the mirrors. You know why? Let me show you why. This is nothing but a plane mirror, but it resembles you. Ask me how. Let me tell you, this is how. All of you are sitting like this. Do not lie to me. I know that. You are, my friend, right now are looking like either a concave mirror or you inverted it look like a convex mirror. Let me explain you how. So, spherical mirrors. I have a plane mirror. Okay, I have a plane mirror and I pushed that plane mirror. Okay, I punched that plane mirror. What does this shape says? It's a spherical shape now. It's not plane anymore. I punched it and made it spherical. Very good. Now, if I punch like this, it's spherical. If I punch like this, it will be round, curved in a different direction and all. So that curved surface is a part of a sphere. If I complete it, this surface is part of a complete sphere. So that's why, that is the only reason why it's called a spherical mirror, because it's a part of a sphere. Getting my point? It's part of a sphere, because mirrors are 3D. It's not just a single line like this, right? It has some depth too, right? It has some area to it. So if you complete it, this is a sphere and not a circle. This is a sphere. Now let's study about these mirrors and all. So there are spherical mirrors, again the same thing. The reflecting surface of a spherical mirror may be curved inwards or outwards. Let me tell you how. This is a sphere, the sphere I made. Now the reflecting surface of a spherical mirror, you are understanding how it's a spherical mirror now? Okay. Now let me tell you that the rays are coming from this direction and it hits the inward portion. This is the inward portion, this is the outward portion, right? This is our inward portion. The rays are hitting the inward portion. When the rays are hitting the inward portion, the reflecting surface will be the inner side of the sphere. So the spherical mirror whose reflecting surface is curved inwards. So this is the reflecting surface and it's curved inwards. Rays are coming like this. This is the inward portion. That is faces towards the center of the sphere. Now I made this sphere so it has some center. So it basically is saying that the reflecting surface is curved such that the reflecting surface faces towards the center of the sphere is called a concave mirror. Just like a cave. Let's imagine it's a cave and all the rays are going inside that cave. If the rays are going inside that cave, that is called a concave mirror. Okay? You're done with the concave mirror. Now let's see what a convex mirror is. Convex mirror is just the opposite of concave mirror. The rays are going inwards of a cave. If the rays are hitting on the other side, this was my concave mirror if it's reflecting from this side. If the rays are coming from this side and it's bouncing back from this curved outwards surface, then it is called a convex mirror. The spherical mirror whose reflecting surface is curved outwards, meaning this is the reflecting surface, this is our outward surface. Okay, this is our outward, or let's just don't say it outwards, let's call it the back side of the mirror. It is the back side of the mirror, and the front side is the one which is curved outwards. It is outwards, correct, and is called a convex mirror. So if the rays are going inside a cave, it is called concave mirror, and if the rays are hitting on the outward side of the spherical surface, then that mirror will be called as convex mirror. Okay. Now there are some terminologies for these spherical mirrors. These are very important. This is a very important topic. Do not skip this. Now let's just study very quickly. So this C is called center of curvature. Center of curvature. Curvature is nothing but this part, like how much our mirror is curved. So this, now we know, I have told you it's a part of a sphere. So I completed the sphere, and the center of that sphere, the center of that sphere is called center of curvature. Now the 2 or 3 main points. The center, we have this mirror and this center point. This center point is this P, and we call it as pole. We call it the center of our mirror, curved mirror, is called a pole. Now this F, which is what? From pole to the center of curvature is our radius. Can I call it radius of curvature? So R is radius of curvature. Perfect. Okay, now this R is radius of curvature, C is center of curvature, and P is our pole. If we half, this is my radius of curvature, if I half this distance, then the center point of this distance, this is called the focus of mirror. It is called what? The focus of mirror. F. They say F is the focus of our spherical mirror. Perfect. Now, just like this is radius of curvature and this is center of curvature, the same way this is a focus, and this distance, the distance of focus from pole, this distance is called focal length, and we denote it by small f. Focus of mirror is capital F, and the focal length, the small f, is called the focal length of mirror, and we denote it by small f, focal length. Okay, that is pretty much it. This, the central axis, the axis which is passing through the center of curvature, which is probably we can say the diameter which is passing from the center of curvature, is called our principal axis. And we say this as hollow sphere because the solid sphere is one which has matter in it. Hollow sphere just has the outing. So we cut a part of the hollow sphere and called it as our spherical mirrors. There is one more thing known as aperture. Aperture is just the length of see, this is our whole sphere, but the whole sphere is not the mirror. The reflecting part is just this much. So this part is called aperture. This part is called the aperture of the mirror. Great. Now, okay, so our main topic was image formation. We saw image formation by plane mirror, then we saw what concave mirror and convex mirrors are, and then we saw some terminologies for those mirrors which will help us form the images later. Okay, now a very important topic, image formation is starting. Please be very attentive. Now there are rules, some rules for images formation, there are rules for everything, but don't break these rules, please. Now the main rules for image formation in, first study concave mirrors. We'll study concave mirror first. So there are few rules that you just keep in mind, and there will be nothing else that will stop you from making a perfect image. Okay, the first rule is, when a light is coming from infinity, when a ray of light is coming from infinity, what it does is it reflects from the mirror surface, and it goes back from the focus. In here we studied that this is the focus of a spherical mirror. So when a light ray is coming from infinity, it always passes through the focus of that mirror. It passes through the focus of that mirror. Perfect. This is our first rule. Okay. The second rule is, now if a light is coming through focus, it will reflect back and goes to infinity. Almost the opposite thing. Coming from infinity, travels back from focus. Here it is coming from focus, it's passing from focus and reflects and goes back to the infinity. It's coming from, okay, very good. Now this is our second rule. These are the rules that you should follow. If you kept these 4 rules in your mind, your images will be perfect. Now the third rule is, now I've told you one more thing. What was that? Center of curvature. Every mirror has center of curvature. So if a ray is passing through center of curvature, it will reflect, it will hit the mirror and reflect back from, and it again will pass from the center of curvature. It comes back and goes back, it comes and goes back the same path. It will pass from the center of curvature, reflects from the mirror, goes back, passing from the center of curvature again. This is our third rule. Our fourth rule will be, it is very important. Now what is the first law of reflection that we studied? Ma'am, the first law was that the angle of incidence will always be equal to the angle of reflection. Now what will happen? The ray which is coming, now we saw that ray coming from infinity, passing from focus, passing from curvature. What if the ray is not passing from any of these points? What if just randomly hitting our mirror at any point? What will happen? If the ray comes from any angle, and it will make the angle with what? This radius of curvature, it will make the angle with our principal axis. It is making angle I. Okay, so it will reflect back with what angle? With the same angle it came with. It hit the mirror with an angle of I with principal axis. Then it will reflect back. And will make the same angle R with the principal axis, and this this angle I will be equal to angle R. Okay, and this is hitting the pole. If it's hitting our pole, that means the incidence ray is hitting the pole and it reflects back at the same angle. So I equals to R at pole. Okay, at pole. Very good. Moving on, now let's use these rules to see how we can form the images. Okay, let's say our first case is our object is at infinity. So from infinity we saw that rays will always come parallel to the principal axis. Okay, the rays will come parallel to the principal axis and will pass on the focus. Now, parallel to the principal axis, the rays will always come parallel to the principal axis from infinity and it will pass from the focus. Okay. So now we are given a situation that assume you have a concave mirror and your object is at infinity. It's far away. So from infinity, all the rays always comes parallel to that mirror, parallel to that principal axis. So from here, we'll draw just these lines. Okay, the rays are coming parallel to the principal axis. I've made some pretty bad rays. Okay, this is coming parallel to the principal axis. Now what is the first rule? If the rays are coming from infinity, it will always pass through focus. So it will reflect back. This is our focus, this is our center of curvature sorry, and this will pass through, this will pass from the focus, and our image will be formed at focus. Now there are some important points of the image that is being formed. The image formed by a concave mirror is real. Real means what? I told you last time, in the case of plane mirror, the rays were not actually converging. They were not meeting at a point. They were appearing to come from a certain person. So the image was virtual. But here, the rays are coming from infinity. They are getting reflected and they are actually meeting at focus. So when the rays actually really meet at focus, that is called a real image. Also, the image in case of concave mirror is inverted. In case of real image, the image will also be inverted. Inverted means that my head will look downwards and my feet will look upwards. Okay, and at this point, what can we see is the image is point sized. Okay, it's just a point of image that is being made here, right? So the image will be real, inverted and point sized. That is our first case. Very good. Let's go to the second case. Now my image was very far away. So what they did is, they pushed the image close to the mirror. This is my mirror. The image was very far away. What they did is, from infinity, they brought the image somewhat closer to the mirror. Now what we'll do is, beyond C. This is our C. This is our focus. Now we'll place our object beyond C. Let's place our object here. Okay, let's place my object here. Now the one ray will go back parallel to the principal axis. Very good. And since it's parallel to the principal axis, it will reflect back and will pass through focus. Correct? Until this, everything is fine. Now we study one more law here. What was it? That the incident ray will hit the pole of the mirror and will reflect back at the same angle. So we study one more rule, that the incident ray that will hit the pole will reflect back with an angle R, which is equal. Angle of incidence is equal to the angle of reflection. So from the top of this object, a ray will be incident on pole. This is pole. Okay, wait. From this pole, from this object, a ray will get incident on pole and it will reflect back with the same angle. What it will do? It will reflect back with the same angle. Understanding? And thus the image will be formed. So moving on to the next image. Now our image was at infinity. So what we did is, we brought that image a little closer to our mirror. So instead of infinity, now we placed our object beyond this C. C is what? C is our center of curvature. F is our focus and this point is called our pole. So we placed our object at beyond this C point. Okay, now what happens is a ray will go parallel to the principal axis. Okay, this is our principal axis. A ray will go parallel to this principal axis, hits the mirror and will come back and will pass through focus. Okay, this we knew from our very first rule of image formation from concave mirror. If the image is coming from infinity, the rays are parallel. So for any parallel ray, that ray will reflect back and will pass through the focus. Now the another fourth rule, what was it? The ray will hit the pole, the point pole, and will reflect back at the same angle. The ray will hit the pole and thus will reflect back at the same angle, and this is where our image will be formed. Now this is very crucial. See it properly. The head of the image, the rays which are passing from the head of the image, let's say this is A and this is B. The rays which are passing from point A are converging at this point. Let me call it as A dash, are converging at this point. And if the ray from this point is going like this, it will come back at the same angle as it parallel to the normal, so there will be no deflection. So it will go parallel to the normal and come back in the same direction. So the tail of the object will lie on this principal axis only. Okay, so can you see now how the image is inverted? The head of the image, which was above before, now lies below the tail of the object, and hence we can say that our image is inverted. Now you understand the concept of inverted image. Now these rays are real, they are meeting in real, so the image will be real. Okay, and also this object, this image will be a bit diminished. Okay, and where this image is forming, the main point, when you keep the object beyond C, when you keep the object beyond your center of curvature, the image will form between your center of curvature and focus. The image will form between C and F. Okay, understanding? Let's move on to the next slide, which is now, since it was first at infinity, our object, then we brought it a little closer beyond C. Now we brought it a little closer, which is exactly at C. So this is our focus, this was our center of curvature, this was our pole, correct? What they said is the object is exactly at the center of curvature. Now where the object is exactly at center of curvature. This is our object now. Okay, clear? Now again, one ray will come parallel to the principal axis. This is our principal axis. One ray will come parallel to this principal axis, and where it will pass from? It will pass from the focus. Now where will the another ray come hits the mirror from? It will hit the mirror at this pole. So the ray is coming and is hitting our pole. Please use scale while you are making these ray diagrams. This will hit the pole and then it will go back. Let me clear this. The parallel, it will go back from here, and since this will reflect back at the same angle, so it will reflect back at the same angle. Now this object is made at the center and the object was at was placed at the center of curvature, the image formed also was formed at the center of curvature. Okay, so if our object is placed at C, our image will also form at C. Now again, real rays are meeting. The arrows are very important. Okay, the real rays are meeting, so the image is real. Again, from the head, the rays are meeting downwards, so the image will be, yes, inverted. And in this case, if the object is at C, the image will be of same size as that of object. Perfect. The image will be of same size as that of object. Now we brought again the object a little bit more close to our mirror, which is between the center of curvature and our focus. So our object lies somewhere between the center of curvature and focus. Now again, first rule, a ray comes parallel to principal axis, passes from the focus. Then the second ray, it hits the mirror at pole, it passes at the same angle, and see where they are meeting now. They are meeting, let's extend this principal axis, they are meeting somewhere here. So again, if a ray goes like this, it will come back exactly like this. So the head will lie at this principal axis only, and this is the rays coming from the head of the object, the tail, and this is the head of the object. So the arrow will come downwards now. And the tail will remain on the principal axis. The arrow has come down. Again, real rays are meeting, so the image is real, and the arrow is downwards, so the image is inverted. And can you clearly see how that the image formed is bigger than the object? So it will now be magnified, or we can say it is enlarged. So when the object is between our center of curvature and focus, between C and F, the image will lie beyond C. The image will lie beyond C. Perfect. Let's move on to the next image. Perfect. Let's move on to the next image formation, which is at focus. Again, we brought that object a little closer. First, it was at infinity. Then it was beyond C. Then we brought it at C. Then between C and F. So now at F. Okay. So this is our object. Now the parallel ray will come, and it will pass back through focus. Okay, very good. So again, a ray will come which will pass from the pole, okay, and it will go back like this. Now, do you remember that when coming from infinity, the image was being formed at focus? The image was formed at focus, at F. So when coming from infinity, the image was formed at focus. So when the object is at focus, the image will be formed at infinity. The image will be formed at infinity. Just swapped it. When the object is at focus, the image will be formed at infinity. Now, since can you see there was this at C, the size of the image was same as the size of object. Then when between C and F, the size got a bit large. So when the object is at focus, the size of the image will be extremely large, large. And since all the images were formed by which were formed by the concave mirror were real and inverted, so this one will always also be real and inverted. Okay, understood? Then the next image, we brought it, the object, we brought it more closer to the mirror. Now this is between F and P. Now this is a very important case, be very attentive. So this is our F, this is our C. Now the object is between F and P. So let's say this is our object. Okay. Now again what will happen? From this, a ray will go and hit the pole and will come back. This is okay. Now we study one more this one. We study one more rule of image formation by spherical mirror is that the ray which is passing from curvature will go back, will reflect and go back through the curvature only. So we study one more rule of image formation, which is that the ray which passes from the center of curvature reflects and goes back from the center of curvature as well. So in here we will use that law. So what we'll do is we'll pass this line through center of curvature. It will go like this. It seems like it's passing from the center of curvature, so it will follow the same rules. It will reflect back, goes back to the from the center of curvature. Now these rays are, can you see these rays are going apart, so they won't form a real image. But what we see in this phenomena, that these rays go back behind the mirror and they meet at a certain point behind the mirror. This is where these rays are converging. Just a minute. Now if you see, these rays are appear to coming from back of the mirror. So we see what happens if we extend these rays backwards. If we extend these rays backwards, we see that they are meeting at a point and thus making an enlarged image. Now see very carefully what is happening when the object is between the focus and pole. We are making an image not in front of the mirror that we were doing in all other cases of concave mirror. We are making the image is being formed behind the concave mirror. So notice the first thing, when between F and P the image is being formed behind the mirror. So it appears that the rays are converging behind the mirror, but the actual rays are not converging behind the mirror. They are going apart, they are coming back. So in this case the real rays are not making the image, the virtual rays are making the image. So our image will be virtual. Also now the image is also straight, erect. The image is not inverted. The head is upside here and the tail is downside, just like the object. So this is our instead of inverted, our image is erect here, and also you can see the image is enlarged. So when the object is between focus and pole of a concave mirror, it does not make real, inverted or diminished image. It makes virtual, behind the mirror, erect, straight and enlarged image, which is unlike any other case of concave mirror. So these are the 6 cases of image formation of concave mirror. Let's see. Let's just revise them early. Coming from infinity, the image is being formed at focus. Beyond C, the image is being formed at C and F, between C and F. Then at C, if the object is at C, the image is being formed at C. Okay. Next, we brought it a little bit more closer. If we place our object between C and F, the image is formed beyond C. And then if our object is at focus, the image is at infinity. For all of these, the image is real inverted. The image is real inverted. But for the last case, remember, for the last case where the object is between focus and pole, this should not be focus. The focus will be here somewhere. If the object is between focus and pole, the image formed will be not real inverted but virtual, erect and magnified. Okay, these are the 6 cases of image formation by concave mirror. Now let me give you a brief revision to remember how the images are formed and where those images are formed. Just make this table and it will be, you will remember these ray diagrams forever. You will never forget them. So in the first case we placed our object at infinity, and then in second case we placed our object beyond C. Correct? And in the third case it was at C. Okay, fourth case it was between C and F. Fifth case it was at F, and sixth case it was between focus and pole. Correct? Now let's revise where the images were formed, and you will see a very great pattern here. At infinity, the rays coming from infinity, the image was formed at focus. This we remember very clearly. Then at F, when the object is at F, the image will be formed at infinity. If the object is at infinity, the image will be at focus. If the object will be at focus, the image will be at infinity. Keep looking. If the object is beyond C, the image was formed between F and C. If you remember carefully, when the image was beyond C, when the object was beyond C, the image was formed between C and F. And when the object was between C and F, the image was formed beyond C, at beyond C. And when at C, and when our object was on the center of curvature, the image was also formed at the center of curvature. So these 5 cases are sorted out. At infinity, object at infinity, image at focus. Object at focus, image at infinity. Object beyond C, image between F and C. Object between F and C, image will be beyond C, and object will be at C, the image will also be at C. Now just remember the last case, that is between F and P, the image will be behind the mirror. The image will be behind the mirror. Okay, done. Now in all these 5 cases, our image was real, it was inverted, and it was, in this case at focus, it was point size. It between F and C, it was a bit diminished. At C, it was of same size. You see how the size is increasing, and beyond C, the image was enlarged. Okay, at infinity, the image was extra large. And in here, in the virtual case, the image was also enlarged. Okay, there's one more way you can remember this, which is, now I've shown you the trick part, right? How you can remember at focus, the image will be infinity and all that. Now how you can remember this, picture wise, just make a mirror. Okay, this is our concave mirror. This is a rule of 1, 2, 3, 4, 5. all you have to remember is this. This is our focus, this is our center of curvature. So where the object was placed? First at infinity, second at beyond C, third at between C and F, fourth at third at C, okay, first at infinity, second at beyond C, third at center of curvature, fourth at between C and F, fifth at F, and okay, that's it. Understood? These are our 5 objects, 5 places where we placed our objects. What you have to do is just swap these numbers, okay? 1 in place of 5, write 2 in place of 4, just write it in a reverse count. 3, 4 and 5. This is infinity. Now see the magic. When the object was at infinity, the image was at focus. When the object was beyond C, the image was between C and F. When the object was at C, the image was at C. When the object was between C and F, it went back to beyond C. And when the object was at focus, it went back to infinity. So the object is moving towards this way and the image is moving back towards this way. Okay, you can take a screenshot of this. It will be very helpful to remember the ray diagrams. Okay, this was our image formation from concave mirror. Let's move forward to the convex mirror. Now what did I say? The convex mirror it reflects from the other end of it reflects from the outer end of the sphere. Again, it has 4 rules, just like concave mirror. The ray coming from infinity passes from the focus. Now you have to see one thing. Since the sphere, if I extend it, the sphere goes this way, right? The sphere goes this way. So the center of curvature of this sphere will not lie in the direction of the rays of object from where the rays are coming from. It will not lie this way. It will lie on the opposite end, because this sphere is getting converted on the other side of the reflecting surface. This is our reflecting surface. But if I complete the sphere, it will complete on the other side. And the center of sphere will be inside the sphere, right? It won't be outside the sphere. So our center of curvature is on the other side from where the rays are coming from. So this is our center of curvature. Now this reflects back. The rays which are hitting the convex mirror, the reflecting side of the convex mirror will reflect back, and it will appear to us as if they are coming from behind the mirror, and thus it is same as concave mirror, but instead of real rays meeting, here we are seeing virtual rays. We see as if the rays are meeting, but the rays are not actually meeting. They appear to be coming from the focus. So the rays coming parallel to principal axis from infinity, they will appear to pass from focus. The reflected ray will appear to pass from focus. Similarly, if the ray is coming from infinity, this is the incident ray. Here this is the incident ray and this is the reflected ray. Here this is the incident ray, the upper one, and it reflects back and it goes, and this is the reflected ray. Now this ray also seems like it's coming from focus, and this ray which reflects back, it seems like it's coming from what? It's coming from infinity. Correct? So if the rays are incoming ray is directed towards focus, it will reflect back and it will appear that it's coming from infinity. Third, again, if a ray is appearing to pass from the center of curvature, it will go back and come back the same path, and it will appear that it is passing from center of curvature. Okay, now again the fourth rule you remember, right? If the ray is hitting the pole of the concave mirror, it was reflecting back at the same angle. So in here also, if the ray is hitting the pole of the convex mirror, it will reflect back with the same angle, which is known as, so angle I will always be equal to the angle R. Now let's see, in this convex mirror you don't have much cases, just relax back. Now you have learned about the concave mirror, just relax back and see the magic. Now you will yourself guess how the image will be formed. So let's do this, the infinity one first. Now we know, ma'am, the rays coming from infinity will converge at focus. So the rays coming from infinity will reflect back. But since it's a convex mirror, it will appear that they are coming from focus. So this point will be our focus. So to us it will appear that in convex mirror also the image is being formed at focus but behind the mirror. In this case the image is not real and inverted, it is virtual and erect. And since it's at focus, all the rays are getting focused. So this is point size. And it just has one more case, that at infinity and anywhere on the principal axis. The other case is anywhere on the principal axis at any point on the principal axis. So again one ray will come parallel to the principal axis and will reflect back, and from where it will appear to be reflecting back to us? From focus. Very good. Parallel, reflects back, appears as if it is passing through focus. Now the other one is center of curvature. So this ray is hitting center of curvature and it's coming back to the same path. So these two virtual rays are passing from each other at what point? This point. So this will be our object. Now again in this, real rays are not meeting. It is appeared to us that the rays are coming from that point. So these are virtual rays. So the image is virtual. And can you clearly see that image is short in size? So the image is diminished. Okay, so virtual, and the head of the image is up, tail is down. So what? It is erect. Great. So now we have done image formation by concave mirror as well as convex mirror. So congratulations, the ray diagrams are completed. I hope you remember all this. It's not very tough. Just revise it twice or thrice at least. I won't tell you that with this one shot you will just, it will just act like that bread that Doraemon has, that you write everything and you eat it. No, you have to practice. But if you see this and then you'll practice, you'll remember this in one go. I've told you all the tips and tricks to remember these ray diagrams. Just keep them in mind. Keep the basic rules of image formation in mind and you'll be all sorted. Now, just we'll see one more topic. Now, what are the uses of, we read all these concave lenses, convex lenses, how the images are formed. But ma'am, where exactly these are formed? Why are we studying this? Oh my God. When you go to parlor, when you get your beard done, when you do your makeup, what you want, a normal mirror or you want a mirror that is a bit magnified so that you can see that one strand of hair left. Right? So you need a mirror which enlarges your image, your hairs, which shows you an enlarged image. That is where we use concave mirror, because we know if we place our object between focus and pole, that is very near the mirror, it will form a enlarged image. See, if we place it between focus and pole, it will form a enlarged image, and so that we can see how our makeup is done. Okay. The next part, and there are many more examples, headlights of vehicles and solar furnaces. The sunlight is coming from infinity and is getting focused at that focus point, and hence our food is getting, the furnace is getting heated. And then dentist mirrors, again they need a large image to focus on your teeth, and telescopes, because the rays coming from the planets or the moons, we want to focus them on a particular place. So they're collecting so many rays and focusing them on a single point. And that's how we see amazing planets. We are able to see amazing planets, amazing perfect moon and all. This is concave mirror. Uses of convex mirror are some vehicle side mirrors. Now convex mirror did what? It diminished the image. So we have these big trucks and big cars going around on our streets. So we want to see them all, right? We want to see where they are going, how they are approaching us or not. So convex mirror diminishes the size of that truck, and hence in that small screen we are able to see so many 2-3 cars or these big trucks, etc. And then again in security, surveillance, road safety, parking areas, and those pee holes in your doors, they also diminishes the size of the object, right? Now now we have studied how the image is formed, but there is one important topic left, which is the sign convention. It is very easy, very easy. Just listen to what I'm saying. This is our concave mirror. This is our concave mirror, and this inward side is the reflecting side. Now when we were placing an object, we always placed the object upwards, up on the upper side of the principal axis. This is principal axis. We always placed our object on the upper side of the principal axis. So let me tell you the sign conventions now. There is one more basic thing you need to remember. This is our mirror. From the mirror, the left hand side will always be taken as negative. The right hand side, anything which is at the right hand side of the mirror, will always be taken as positive. Just like your x-axis. If you have this axis, you take this as positive and you take this side as negative. Correct? Just like that. The left hand side, anything which is in the left hand side of the mirror will be taken as negative. Anything which is at the right hand side of the mirror will be taken as positive. Second, anything which is above the principal axis. Above the principal axis will be taken as positive. Anything which is placed downward side of the principal axis will be taken as negative. Now, left side of the mirror, negative. Right side of the mirror, positive. Very good. So, now object was always placed on the left hand side of the mirror. So, the object will always be, the distance of the object. The distance of the object, sorry, not this. The distance of the object will always be taken as negative. This one. The distance of the object will always be taken as negative. Both in convex mirror as well as concave mirror, the distance of object will always be negative. Now, when we were forming an image on concave mirror, using concave mirrors, the images were formed on the same side of the object, and those images were real and inverted. Let me show you these. Real and inverted, real and inverted, real inverted, real inverted. All the real inverted images were formed on the left hand side of the mirror. left hand side, left hand side, left hand side, left hand side. Okay, so if the image is real and inverted, if the image formed is real and inverted, the distance of that image will be negative. Okay, but if you remember that in one case, when you place your concave mirror so close to your face, the image was being formed at the other side of the mirror. The image was formed at the other side of the mirror. Now this is our image and it is formed in the right hand side of the image. So at right hand side, we know the convention is to take the sign as positive. So the right hand side image was virtual and erect. So for virtual and erect, the image will be positive. The image distance will be positive. For real and inverted, the image distance will be negative. And let's see, the focal length will be on this side. The radius of curvature will be on this side. The focal length is in left hand side. For left hand side, focal length is negative. Radius of curvature, left hand side. For left hand side, the radius of curvature is negative. Height above the principal axis positive, height below the principal axis negative. Okay, easy. Moving to the convex mirror. Now this is our opaque side and this, the outer part, is our reflecting side. Now in here, if you remember, the focus was on this side and the radius of curvature will always be on this side, also be on this side, and this is our right hand side. Right hand side we take positive. This is our left hand side. Left hand side we take distances as negative. For height above the principal axis positive, height below the principal axis negative. Now in here also we placed the object on the left hand side. So the left hand side object is negative. Okay, and in convex mirror, the image was always formed on this side of the mirror, right? And this side is, and the image was always virtual and erect. Virtual and erect. So on right hand side, for virtual and erect image, the convention will be positive here. Now its focal length is on which side? Right hand side. So focal length on right hand side means focal length is positive. Radius of curvature on right hand side, radius of curvature is positive. And the same, height above the principal axis, height below the principal axis, positive and negative. Let's see one more thing. For concave mirrors, just remember this slide, okay? For concave mirrors, for 5 cases, the image was formed as real and inverted. Okay, and it was of different sizes. It was of size bigger than it, smaller than it, and everything. With real and inverted, we have different sizes for different placement of object. But in one case we had virtual and erect image. We had virtual and erect image behind the mirror, and for this particular case, the size of our image was enlarged. Okay, so concave mirror always forms real inverted images for 5 cases, but for the 6th case it forms virtual and erect image which was enlarged. Now here is the one thing to remember. For convex mirror also forms virtual and erect image. Virtual and erect. Yeah ma'am, but concave mirror also forms virtual and erect image, and convex mirror you are saying also is forming virtual and erect image. So how will we differentiate that which image was formed by concave and which image was formed by convex mirror? Very important, very good. So in the case of concave mirror, the virtual and erect image formed was enlarged. It was enlarged. It was bigger in size. But in case of convex mirror, the image will always be diminished in size. Diminished in size. It will always be smaller than the object. Okay. In case of concave mirror, virtual and erect, enlarged. In case of convex mirror, virtual and erect, but small. Now you will remember this. Very good. So moving on, we have this formula which even NASA uses still. You know, on our satellites we have these mirrors, big mirrors that are reflecting light from sun, sending it back to earth and all, and they uses the same exact formula for mirrors. Now let's see, it's a very basic formula, mirror formula we call it. It is 1 by f equals to 1 by u plus 1 by v. Now what is this u, v, f? This f we studied. This is our mirror and this was our focal length. If we place this object here, the distance of object from the center of the distance of object from center of the pole, the distance of object from center of pole will be u, and if the image is formed, let's say here, so the distance of image from the center of pole will be v, will be written as v. So they are saying that 1 upon focal length of mirror will equal to be 1 by object distance from the mirror, object distance from the mirror plus 1 by image distance from the mirror. This is just very basic, very simple mirror formula. See, the f is focal length of the mirror, u is distance of the object from pole, and v is the distance of image from the pole. Now we'll do some very important numericals for this, just stay tuned for that, okay? Now next, there is one more thing that we studied in all that image formation was, ma'am, the sizes in all the placement of objects were different. In some it was big, in some it was small, in some it was same. So this difference in sizes, we call it as magnification. We call it as magnification, and we have one formula for this, which is the height of image. This is height of image. Hi is height of image divided by height of object. Height of object, which is equal to the negative of, don't forget the negative of v by u. V is what? Distance of image from the pole, and u is what? Distance of object from the pole. So magnification is height of image by height of object, or minus of distance of image from the pole divided by distance of image from the object. Very important. This is very interesting. You will enjoy this. Now we know the images are real, inverted, virtual, erect, diminished, enlarged, and all the thing. Now you can derive all that from just the value of magnification. You just have to remember these small particular rules, and these are not very hard. We know if the magnification is greater than 1, it will be magnified. Let's say my magnification is 2, which means the height of image is greater than height of object, right? It basically means that height of image is greater than height of object, so it will be enlarged. If m is less than 1, the image will be diminished. If the m is positive, our image will be virtual and erect. Now let me tell you how interesting this is. How can we see this? Now we have minus v by u, right? Let's say my image is virtual and erect. If my image is virtual and erect, then it is making in the, this is our mirror, virtual and erect image was made from on which side? This right hand side, right? For virtual and erect, the V was positive, and we know U was always on left hand side, so the object was always on left hand side, so the U is always negative. If I put that value, if I put V here and minus U here, there is one minus here already. I put V, this is for virtual and erect, and U is minus, this will cut. So the magnification is positive. Now there is no negative sign, magnification is positive, so we have positive for virtual and erect. Now one small difference, in real and inverted, the image was also forming on the right hand side, so the V was actually minus V, because on left hand side the image was also formed on the left hand side, and in left hand side our convention is negative. So for real and inverted, I will write minus V, and there is already a minus outside, so I will write like this, divide by U is always negative, so divide by minus U. So I cut this minus with this minus, there is still one minus left. So this means in real and inverted case the magnification is negative. You understand it, right? So if greater than 1 magnified, less than 1 diminished, positive virtual and erect, magnification negative real and inverted. If it is plus 1 minus 1, it's of same size. If magnification is 0, it is of point sized. Now let's do these similar things. Let's see which mirror these, which of these magnifications have concave mirror, convex mirror, real, inverted. Let's see. So M is plus 2, which is, let's write positive. The magnification is positive, it is greater than 1. So what happens is magnification positive, positive meaning it is virtual and erect, virtual and erect, and magnification greater than 1, so it is enlarged. And we know that virtual and erect images was formed by both concave and convex mirror, but with convex mirror the image formed was diminished, but with concave mirror the image formed was enlarged, and here it is enlarged, so this is concave mirror. Correct? Let's go. Second, minus 2. Now this is negative and it is greater than 1. Okay, 2 is greater than 1 and it is negative. So it is what? For negative we have real and inverted. Now don't understand that it's minus 2, ma'am, it is less than 1. We are seeing the negative sign different than the numerical value. For negative sign it is real and inverted, and since 2 is greater than 1 so it is again enlarged. But you don't even have to see when there is a negative sign. Whenever there is a negative sign in a magnification, it is real and inverted. Convex mirror do not form real and inverted image, so it is always concave mirror. Perfect. Now this is minus 2. Array ma'am, this is minus, again concave mirror, but here half is less than 1, right? So it is diminished here. Diminished image with real and inverted. Real and inverted and diminished was formed by concave mirror. Now plus half. Now ma'am, this is for plus, we have to see plus because we have virtual and erect. Now concave and convex both form the virtual and erect, but this is less than 1. Half is less than 1. Virtual, erect, diminished. But concave mirror only forms the image which is virtual and erect and enlarged. Here we are getting virtual, erect and diminished. So again this will be the 6th case of concave mirror between focus and pole. sorry. This will not be in focus and pole, the image will be enlarged. So this will be convex mirror, because convex mirror always forms virtual, erect, diminished. This is diminished, so this is convex mirror. Perfect. And this is how our reflection part ends. Let me just show you a easy numerical. Now this is where our reflection part ends. Let's see a basic numerical to get a gist of what we will be dealing with. Now we'll do all the difficult ones, all the board numericals later in a different video. Let's just see a basic numerical for now. So for numericals, there is one tip: read the numerical very slowly with proper attention. It will take 1 minute more, but you'll solve the numerical in a much less time than you will if you just go through it without understanding it. As you read the numerical, just write down what you understand. Okay, let's see. So an object, what it says is, an object of 2 centimeter height is placed at a distance of 16 centimeter from a concave mirror. Now, what did you read till now? An object of 2 centimeter height. So, the height of our object is how much? 2 centimeter. Till now, you have read what the height of our object is. It is 2 centimeter. Distance of 16 centimeter. Now, distance of object. So, distance of object is u. So, u is 16 centimeter. Now, from a concave mirror. Now, from a concave mirror. Keep this in mind. We have concave mirror. What kind of image does a concave mirror forms? It forms, ma'am, both real as well as virtual. So we will see in this case which kind of image it is forming, a real or a virtual. It is given in the numerical which produces a real image. So now we know that we are not dealing with a virtual image, we are dealing with the real image. So again, image height is also given, real image of 3 centimeter. So height of image will be 3 centimeter. All of this is given in the numerical. Now, what is the focal length of the mirror is what we have to find. So, for focal length, let us write the formula first. What we know, we have to write first. So, ma'am, from mirror formula, we know that 1 by focal length equals to 1 by u plus 1 by v. Now, we have u, but we don't have v. So, how can we find v? Now, we know one formula, one relationship between magnification, height of object, height of image, and distance of object, distance of image. What was that? Our magnification was height of image by height of object, which was also equal to minus of v by u. So, we are given height of image, we are also given height of object, and we are also given distance of object, which is u. So, by using this formula, this relationship, we can find the value of v. What will it be? Height of image is 3 centimeter divided by height of object is 2 centimeter equals to, we have minus v which we have to find, and we are given u as 16. So, from here we will be what? We will be also the object, distance of object we know is always taken in negative. Remember that, right? So, this will be minus 16. So, here we will write minus 16. So, we will be 3 into 16 divided by 2, and here we have a this minus sign will get cut. So, we have just a positive v. Now, v will be 24 centimeter. V will come out to be 24 centimeter. Now, here is a little tricky part. We are given that it forms a real image. Real image in case of concave mirror was always formed on the left hand side of the x-axis. when we form an image, the real image was always formed on the left hand side of the concave mirror, and we know the distance which are on the left hand side of the mirror are always negative. So the real image formed by concave mirror always have negative distance of image. So here we will be taken as minus 24. How did we decipher that it's a real image? It is given in our question. So we have now V, now U was given, we have our V, we'll find our focal length. Let's do that. 1 by F equals to 1 by U plus 1 by V. 1 by U is minus 16 and V is minus 24. Is it correct? We'll take just the minus common. It will be 1 by 16 plus 1 by 24. We can just take the LCM, which is 48. Okay, so 16/3 is 48 plus 2. So our focal length will be minus 5 by 48. Now remember, this is not the focal length. This is 1 by focal length. For focal length, we have to reciprocate it. So for focal length, the focal length will be not minus 5 by 48, but minus 48 divided by 5. Okay, which will be 9.45. So 9.8 centimeter. So our focal length will be 9.8 centimeter. Understood? This, find the position of the image. So we have minus 24 centimeter. Let's just make a diagram of it. Now the next part is find the position of the image. To find the position of the image, let's make a diagram of it. So our U was given as minus 16 centimeter, V came out to be minus 24 centimeter, and our focal length came out to be minus 9.8 centimeter. Now if this is our concave mirror and our focal length is at 9.8, our U is, so if focal length is 9.8, what will be the radius of curvature? It will be double of this, which is 19.6 centimeter. Okay, now the radius is at 19.6, the focal length is 19.8. Now our object is at 16 centimeter, which means it is between our radius of curvature and focal length, somewhere in here. Okay, and our image is now beyond radius of curvature, which is 24 centimeter. So image is somewhat here, 24 centimeter, and our object was 16 centimeter. And this is what we studied. If the object is between, this is the object, if the object is between curvature and focal length, the image form will be beyond the radius of curvature. So hence proved, all the image formations were right, our formulas are right, our calculation is right, and thus if the object is between so the object is, if the object is between center of curvature and focal length, our image will be beyond the center of curvature. So the answer for this is, find the position of the image. Our position of the image will be beyond center of curvature. Okay, we are done with the numericals. So this is where the reflection part ends of this chapter, and we'll move to the next part, which is very exciting. Now we have studied the reflection of the light. The next part of this chapter which we are going to study plays really weird, really good tricks on our minds, which bends our minds like how this can even happen. What I'm talking about is, if you've ever gone for swimming, you must have seen that when the person goes into the swimming pool, they look short, right? Or sometimes in the weird cases, their heads might look displaced. Look, the body is here, but the head is displaced. Or if you have looked through a glass, if you place a glass in front of you filled with water, the next person might see that your eyes are enlarged, or your mouth or your nose is enlarged. Why that happens? Is it magic, or maybe it's just light playing tricks on our minds? Let's study that. This are those examples of refraction you have seen. Now why this happens? Why? When we see light through something, through water or through glass, why it appears, the object appears like this, whether they are displaced, whether they are magnified, or this light which is playing really great tricks on us is not magic. We know that it's not magic, but some phenomena of physics, and that phenomena is, my friend, is called refraction. Now what that phenomena is, if we just name it, it's refraction, yes, but what that phenomena actually is, what is refraction? So refraction in physical terms, in physics, what we say is the bending of light when it passes from one medium to another, but those mediums should have different density, is called bending of light, is called refraction. Yeah, it's called refraction. But how that happens? Why that happens? Basically because of the density. In water, the atoms and molecules of water, H2O, is placed in a different orientation than the oxygen molecules in our air. So when the light, we know the light hits the particles and it comes back in reflection. In refraction, light hits the particle and gets bent. It changes its direction. So if the particles are different, when the light hits different particles, it will bend differently. Same happens in refraction. When the light hits air molecules, it bends differently. When the light hits water molecules, it bends differently. When the light hits glass molecules, it bends differently. And we'll see how exactly that happens. So to understand that, let's see this very important diagram. Now, this is basically the diagram for refraction. If someone asks you what refraction is, you have to definitely explain this diagram. Now, this is not the rarer medium. This is the upper one is our rarer medium. Okay. So what happens is, we are assuming in this case that light is coming from rarer medium to denser medium. That are now air, we have air. Air is definitely rarer. Air is definitely rarer than water. We know the density of water is definitely more than air. So if the light is entering from air into the water, that is mean that the okay. If the light is entering from air, that is the rarer medium, into the water, that is the denser medium, what will happen? The light will refract differently in rarer medium and denser medium, and we'll see how. Let's say our light ray is coming from the air entering into the water. So water is denser medium, air is definitely the rarer medium. So let's say this is our ray. This is our light ray and is being incident on this point. Any point on the water surface, it is getting incident. Now what happens is, in case of mirror, it was getting reflected. But it is water, it will go inside that water definitely. So water is denser medium. Now what happens is, instead of going straight like this, it should have gone like this, but instead of going straight like this, it bends. Where does it bend? Does it bend upwards? Does it bend lower? Now from going rarer medium to the denser medium, the light will bend towards the normal. What is normal? We studied in the reflection part that on the incident point, we make a normal to that surface, which is, normal is basically perpendicular to that surface. Now the same in refraction. We make, this is the surface of water, so light is being incident on the surface of water. So what we do is, we imagine, we cannot draw normal on the water, we imagine the normal to the surface of water. Now we extend this downwards. Now when it enters into the water, instead of going straight, it bends towards the normal. What it does is, from rarer to denser, it bends towards the normal. Where? Towards the normal. And if it's going from denser to rarer, in here it's going rarer to denser, that is air to water. Now if the light is going from water to the air, which what that means, from denser medium to the rarer medium, then what will happen, this light will bend, instead of bending towards the normal, it will bend away from the normal. Let's just say this is a ray going from denser medium to rarer medium. We'll make a normal at the point of incidence, and thus this will, instead of bending towards the normal, this should have been its original trajectory. This should have been its original trajectory. But instead of going straight, and instead of bending towards the normal, it is going from denser to rarer, so it will bend away from the normal. This was bending towards the normal, and this is bending away from the normal. Okay, understood? This is a basic definition, basic phenomena of what is happening in refraction of light. Let's move on to the next one. These are some examples of refraction that we see in daily life, which are pretty normal, but we just ignore it for the sake of it. If you place a coin in a glass of water, what it appears? It appears to be slightly upward than the actual height of the water, than the actual depth of the glass of water. That is because of refraction. Now the light was coming here, it should go like this, but we'll make a normal at this point of incidence. Now it's going from denser to rarer, so it will bend away from the normal. So this, instead of going straight like this, it bent away from the normal, and it's going like this. Now if you are seeing the glass of water, we'll see the ray of light that is coming outside of the water, coming from a point behind that water surface, and that's why this coin appears to be a little lifted than its normal depth. Same with the pencil. For this, the rays are coming from this point, but instead of going straight like this, and if we make a normal at this surface, instead of going straight like this, they bend away from the surface, and then they appear to come back from a point slightly above than the actual depth of the pencil. Then again, if you see some fishermen, if you talk to them, they'll tell you that they don't hit the fish when they're hunting for fishes. They don't hit the fish at where they see them, at the exact point they're looking at a fish. They won't hit that fish at the point they're seeing the fish, but a slightly lower. So if the fish is visible at this point, they will hunt that fish with a stick. They will point that fish here. They will point hit that fish at this point instead of this. Why? Because they know the phenomena of refraction. They know that if the fish is appearing at a higher point, the actual depth, the actual point where that fish is, it's not this. It is slightly under that position, but because of the refraction, it looks like the fish is upward, but the fish is not actually at that position. It is slightly below that position. Now understood? Okay, moving on to the next. This. So we studied laws of reflection. Now similarly we'll study laws of refraction. What guides the refraction? What happens? What are the points that we should take care of in the refraction topic while the refraction is happening? So first is same. We knew that in reflection, the incident ray, the normal ray and the reflected ray all lies in the same plane. Now just in here, instead of reflected ray, we are talking about refracted ray. So the incident ray, the refracted ray and the normal to the interface of two transparent media. Now in reflection, the normal was to the reflected surface. Okay, in here the surface which is separating our air and the water is called interface. is called interface of two transparent media. Media is what we call the air medium and the water medium. So on that interface, if we draw a normal and the incident ray and the refracted ray all lies in the same plane. That is the basic law of refraction. One more another important law of refraction is when so this was our refraction. This ray is coming, this is normal and it's bending towards the normal. This is rare, this is denser. So this is our incident angle, okay, and this is our refracted angle. Not reflected but refracted. This is our incident angle. It's the same as the reflected one, and this is our refracted angle. So in reflection, what was it? Angle of incidence is always equal to the angle of reflection. But in refraction, what we take is the sine of angle of incidence. What is it? Sine of angle of incidence. The sine of angle of incidence to the sine of angle of refraction, the ratio of sine of angle of incidence to the angle of sine of angle of refraction is a constant. For the light is constant for the light given of a given color for the given pair of media. What it means is that the sine of I and the sine of R, angle of sine of I, sine I divided by sine R will be constant for just a given pair of media. Means for air and water, in every part of this earth, for air and water, the sine of I and sine of R will be constant. But if we change the media, if we instead of water we take some jelly, okay, or we take milk, so for that the sine of I and sine of R will be different than the sine of I and sine of R of water. For air and water, for air and milk. For both, for air of water in USA, for air and water in America, India, it will be same. For air and milk in India and USA, it will be same. But for air and water, for air and milk, both of these will be different. It's just the basic two laws of refraction. All incident ray, refracted ray and R normal lies in same plane. Sine of I by sine of R equals to constant for a given pair of media. Moving on to the next one. So moving on to the next topic, this light which is bending, how much is it bending? When it goes from air to water, how much the light is bending, that depends, that is given by a concept called refractive index. Now what is refractive index? Just the basic how much light is bending is refractive index. Depends on the refractive index. So refractive index is actually the extent of change of direction of the ray of light that takes place in a again given pair of media may be expressed in the terms of refracted index. So the extent of change in direction of the light when it passes from one medium to another is expressed in terms of refractive index. Now on what quantities does it depend? It actually depends on the speed of light in one medium to the speed of light in another medium. Let's say this is medium 1, this is medium 2, air and water. Let's just take it our basic simple air and water. So if V1 is the speed of light in air and V2 is the speed of light in water, so our refractive index will be V1 by V2. But refractive index of what? Refractive index of the medium 2 in which the ray is going with the respect to the refractive index of medium 1. Now let's say if this our first medium is not air, it's water, and then the second one is milk. So the refractive index of milk with respect to the refractive index of water. Here we have just taken air and water, so refractive index of water with respect to the refractive index of air, which will be speed of light in air divided by speed of light in water. Let's just write it. So refractive index of water with respect to air, what will it be? It will be speed of light in air, divided by speed of light in water. Understood? Just N21 will be the refractive index of medium 2 with respect to medium 1. The same speed of light in medium 1, medium 2. And this is the same, the value of refractive index of a given pair of media depends upon the speed of light in 2 media. Okay. Moving on to the next one. Now we've done refractive index. What is absolute refractive index? So let's say what we did in case of air and water is absolute refractive index. How? To be more precise, if we just assume that the speed of light in air is equal to the speed of light in vacuum. That's why we assume air in this part. But actually speed of light is different in air and in vacuum. Okay, so if the first medium is vacuum, which means there are no oxygen particles, no nitrogen, no carbon dioxide in space. Let's say if medium 1 is space, medium 1 is vacuum, then the refractive index of medium 2 is considered with respect to the refractive index of vacuum, and that is called the absolute refractive index of that medium. Let's say the air is traveling from, instead of air, it is coming from vacuum. For basic sense, for right now, we assume vacuum and air to be the one thing. So if the light is coming from vacuum into the water, then that refractive index, the value of that refractive index will be absolute refractive index of water. Absolute refractive index of water, absolute refractive index of our medium, which is equal to, now speed of light in first medium, which is vacuum. Our first medium is vacuum, and in vacuum speed of light is c, which is 3 into 10 raised to power 8 meter per second, divided by speed of light in that medium, which is our, in here in this case, which is water. Understood? Now we'll look into some actual examples in real life of reflection, how it happens. Now we have studied refraction from one interface, from air to water. What will happen? That ray of light does not stop. If our glass of water is not made up of some plastic, some opaque material, if it's transparent, then the ray will not stop inside the water. It will again continue its path. So it will go from air inside the water, and then it will come out of the ray of light will come out in the air again. So we'll see what will happen in that case. So let's say we've just seen, this is the most basic. Incident ray is coming. This is the glass ray. Let's say the glass slab is just a very thick piece of glass, very thick rectangular piece of glass. Now this incident ray is hitting that uppermost surface of the glass slab. It enters into that glass slab. Now we know, of course, the density of glass slab is definitely more than the density of air, so it will bend. Instead of going straight like this, it will bend towards the normal. So this is our incident ray. Instead of going straight, it will bend towards the normal. So this is our refracted ray. Now it will not stop here, since it's glass slab, it's not opaque, the light will continue its path. So continuing its path, it will hit the lower surface of the glass slab. When it hits the lower surface of the glass slab, now in the first case it is going from rarer to denser. When it comes out, the air is again rarer. So now in the second case, it is coming from denser to rarer. What we made? We made two cases. Case 1 says that light is going from rarer to denser. So it will bends towards the normal. Bends towards normal. Okay. Now from the second case is case 2. The second case says that now the ray of light is coming from denser to and going towards the rarer. So it's going from denser to rarer. So what happens when it goes from denser to rarer? It bends away from the normal. We know that when going from denser to rarer, it bends away from normal. Correct? So this refracted ray, instead of going straight like this is our normal, instead of going straight like this, it bent away from that normal and it follows this trajectory. Now something really interesting happened here. When the scientists did this experiment, they noticed, okay, let's see how much the deflection is from the incident ray. When they extended this incident ray, they found out that this emergent ray, when the ray comes out from the glass slab, that is called emergent ray, and this angle which it makes with the normal is called emergent angle. Okay, angle of emergence, sorry. So when they extended this incident ray, they found out that this distance, the perpendicular distance between the emergent ray and the incident ray is these two rays are parallel to each other, and the perpendicular distance hence called was lateral displacement. D is lateral displacement, and they found out that these two rays are parallel. Okay, this was our small topic of refraction from a glass slab. What happens when rays doesn't stop in the denser medium, it goes from rarer to denser and then denser to rarer. Moving on to the next one. Now again, very important topics of our refraction. Now the glasses I'm wearing, the glasses more than half of you are wearing, the glasses you are using in magnifying glasses, in telescopes, all these are working on the phenomena of refraction. They have studied massive refraction topics and then came out with these contact lenses, with the lenses which we are using in such big apparatuses. Those comes with these topic of refraction. These are the same lenses which they use, which NASA uses, which you use in your contact lens and all. So we'll study about that, how the rays will meet. Why, if I'm wearing this contact lens, when I'm wearing this specs, why am I seeing clearly again? Because of the help of these lenses. And just like we saw the image formation in mirrors and spherical mirrors, we will see with these lenses. Okay, so mirrors were of two types, concave mirror and convex mirror. Lenses are also of two types, convex lens and concave lens. Now this is mostly the same, almost the same topic, just there's one tricky part, which is concave lens and convex mirror. Concave lens and convex mirror makes the same kind of image. Concave mirror and convex lens makes the same kind of image. Just the laws of image formation will switch. So concave mirror was converging. It was converging the rays, and convex mirror was diverging the rays. In this, concave lens will diverge, concave lens will be a diverging lens, and convex lens will be a converging lens. That's all. This is, you can just remember, this is our concave lens and this is our convex lens. The shape you have to remember. For convex lens, it's like thicker in the middle but thin in the edges. For concave, it's opposite, it's thinner in the middle and thicker at the edges. Now, just like we studied terminologies for mirrors, we'll see for the lenses, very basic. For this, we had pole in the mirror. This is called O, optical center. O is called optical center. Now, in mirror, we just had one spherical reflected surface. So we had one focus, but in here we have this curved surface too and this curved surface too. Lenses are basically the merging of two curved surfaces. Okay, so this will also have a focus and this will also have a curvature center. Okay, so and this side of the refraction part, this side of the lens will also have a focus which we'll call F2 and center of curvature which is C2. Similarly for this convex lens, there will be two focuses. This will be our optical center, F1, C1, F2, C2. Now till F1 from optical center, this is from actually till the optical center. Till optical center, it's called focal length, R is called radius of curvature, and in here in concave lens, it's again, this is focal length, this is called radius of curvature. That's it, simple as that. Now let's see image formation by concave, image formation by these lenses. Now we studied some rules, right? In here there are also some rules. So if this is our convex lens and this is our, okay, this is our concave lens, what we studied, if the ray is coming parallel to the principal axis, it will pass from the focus. Now remember, in mirror what was happening? The ray was getting reflected, but in lens it will not reflect, it will refract, which means it will change its direction. So here is the focus, we know focus is on both sides, so when it's coming parallel it will just pass through the focus. Okay, for concave also, now this is a converging mirror, this is convex and this is what? Converging, and this is our concave mirror, concave lens, and this is diverging, which means that in here when a light rough ray is coming parallel to the principal axis, when the ray of light is coming parallel to the principal axis, instead of going towards the principal axis, it will go away from the principal axis. And if I'm seeing from here, to me it will appear that this ray is coming from somewhere like this, and this will be our focus. Understood? Now the next rule was what? The next rule was again this one. For this, coming parallel to the principal axis, passing through the focus. If this is passing through the focus, if the ray of light is passing through the focus, if it's coming something like this, it will become parallel. For concave lens also, if the light ray is coming, now this is a bit tricky. See, this is our focus. Now if the light is coming in the direction of focal length, it is not passing exactly from the focus, but to us it's appearing that it's coming towards the focus. So let's say the light is coming like this, so as it will extend like this. So if the light is coming towards the focus, it will just pass parallel to the principal axis. That is okay. Till here the laws are same. Just one more law which says that we have one thing in lens which is different from mirror, which is our optical center, which is the center point of our lens. Now if the ray is passing exactly from the focal length, there will be no change in the direction. If it hits the optical center, it will pass straight in this direction and it will not bend towards any way. For concave lens also, this is our optical center. This is our optical center. If the ray is coming like this, it will go directly like this. These are the three laws we have to keep in mind for our image formation in concave lenses, in convex and concave both. Let's start with image formation in convex lenses. So for convex lenses, we'll place the object exactly where we placed in concave mirror, where infinity brought it a little closer beyond C, at C, between C and F, at F, between F and P. In here it will be just F and O, because we don't have a pole here. What we have is, we have optical center. Now the first case is that the light rays are coming from infinity. The light rays are coming from infinity. Since it's a convex lens, what is it? Convex lens. Now what we are saying, convex lens and concave mirror will form the same kind of image. What kind of image did concave mirror made? Concave mirror made, ma'am, real, it made inverted, and it made all size of images. Okay, so real, inverted. So convex lens will also make a real and inverted image. And in case of the object at infinity, what it made? It made a point size image at the focus. So it made a point size image. So this is our focus. Rays are coming parallel to the principal axis from infinity. They converge, convex lenses converging, they converge the rays at the point of focus. That's it. First case done. Next. Okay, then we place the object beyond C. Now in mirror we called it center of curvature, in lens we just called it 2f1, because anyway center of curvature is twice of focal length. So here we just call it 2f1. Now where is the object? The object is beyond 2f1. The object is beyond 2f1. So where the image was formed? The image was formed between focus and center of curvature. So here the image will form between focus and twice of the focus, f2 and 2f2, beyond 2f1. So first ray will come parallel to the principal axis. This ray is coming parallel to the principal axis, okay, and it will go pass from the focus. We just saw. Second, third rule of image formation: if the light pass from optical center of lens, it will go straight. So if this second ray passes from the optical center of the lens, it will go toward in the same direction without bending. And where this is not 2f1, this is 2f2, sorry. So this object will be formed between f2 and 2f2, between focus and twice of the focus. So this is our object. Now very important again, this ray is where it's going here, and this passing from optical center went straight and meeting here. So the upper part of the object gets inverted, and now the arrow is downwards, because the rays from the upper part are meeting at the lower part. Okay ma'am, but you can also say that the arrow is like this. Why is the arrow not like this? Because the ray from the lower part, if this is the lower part of my object, then the ray will travel parallel to on the principal axis. It will pass from optical center. From optical center it will go straight and it will meet here, not here. It's not the lower part of the object. The rays from the lower part of the object are meeting on the principal axis and not somewhat here. So this is the lower part, this is the upper part. If this is A and this is B, so this will be B dash, this will be A dash, and that's why, my friend, this object is inverted. So what kind of image it formed? We know it formed inverted, and we know the rays are actually converging in real time. The real rays are converging, so the image is real and it is inverted. Now it is of what size? Here the size of the image will be enlarged, because in concave mirror we also know the size of the image was enlarged. Okay, so moving on to the next. Here the object is at 2f1. There we studied the object was at center of curvature. So at 2f1 we knew in mirror when the object was at the center of curvature, the image was also forming at the center of curvature. So here it will also be same. The object was at 2f1, one ray comes parallel, pass from the focus, the other ray passes from the optical center, and hence it passes, extends and meet at the 2f1. Now the image is again real, the image is again inverted, and the image is again of same size. Very good. Understood? Moving on to the next. See how easy it is. You don't have to use too much of your brain. Just remember the basics. Next, now we took the object a little closer. So between 2f1 and f1. Now this is our object between 2f1 and f1. Again one ray comes parallel and gets bent towards the focus, passes from the focus, we extend it, then the second ray goes from the optical center, does not bend, goes straight, meets in the back at this place. Okay, understood? Now in the image will also be real, the image is inverted, and the image will be what? The image is clearly enlarged. Okay, so between 2f1 and f1 the image is beyond 2f2. The image was formed beyond 2f2. And what kind of image is formed? Real, inverted, enlarged. Next, at f1, next case was at f1. Now if the rays were coming from infinity, the image was made at focus. If the object is at focus, the image will be at infinity. Object is at focus, one ray comes parallel, passes from the focus, another ray passes from the optical center, and hence they will just be parallel to each other and the image will be made at infinity. Again the image will be real, image will be inverted, and the image will be extremely enlarged, extremely large. Okay, what will be the next case? Comment down. What will be the next case? Ma'am, what kind of question is this? You just push the object towards the lens. The next object will be between f1 and O, between f1 and our optical center. Now remember the sixth case of concave mirror. What was happening? The image was made behind the mirror and the image was virtual, the image was erect and it was enlarged. So in case of lens 2, in case of convex lens 2, the image will be what? Virtual. Let's just write it first. We know it will be virtual, we know it will be erect because of our previous knowledge, and we know it will be enlarged. Arey ma'am, please tell us first how. Let's see how. Between f1 and optical center, now it will go parallel. Now the actual ray will pass from usually the focus, and it will now also pass from the focus. For optical center, it will pass from the optical center and continues its journey. Now these two rays are actually going away from each other. So if we see the image from that side, what will appear to us? It will appear that this ray is coming back from this ray is coming is appearing to come back from this path, and the ray which passed from optical center appears to come back from this path. Appears to come back from this path, and they do not meet, they appear to meet at this point, and hence we get a virtual, erect, enlarged image. Okay, let's move on to the next. This is the image formation by convex lens. Now see the image formation by concave lens. This is our concave lens, thin from the center, thick at the edges. Now concave lens is similar to convex mirror. In convex mirror, the image was always diminished, it was virtual, it was erect. Now what in case of concave lens, again we know the first rule. The rays of light are coming from infinity. They hit this optical line of the mirror. This is the optical center. They hit the concave lens, and what did I tell you in case of concave lens? The rays does not bend towards the focus, it bends away from the focus. So it goes somewhere like this and it goes somewhere like this. Now if I'm standing here, these rays are not meeting So how can I see that the image is being formed? To me, it will appear that these rays are coming back from a point that they are meeting, that they will appear to meet from at a point which will be our focus. So the image will be in case of this is concave lens. In case of correct. In case of concave lens, the image will be what? Virtual. The image will be erect, and in this case the image will be point size. The image will be formed at focus, first point. The image will be formed at focus. It will be virtual, erect, and it will be of point sized. Understood? Basics, very simple. Moving on to the next. Now, in case of convex mirror, there were only two cases, ma'am, from infinity and anywhere on the principal axis. In case of this concave lens, we'll also see just the two cases, anywhere on the principal axis, on infinity. We saw on infinity. Now we have placed object anywhere on the principal axis. We'll just use our brain and draw and use the basics of refraction, the laws of refraction, which was law of image formation. So one ray will come parallel. Now concave lens, it will not go towards the focus but away from the focus. It will go away from the focus and will appear to come back from focus, from the other focus, and this ray, the other ray, it will pass from the optical center. So this, the one actual ray is meeting and one ray is appearing to come from focus. So these two rays will combine and make this object. Now this object is real. This image is, the image formed by the concave lens will be real. Will be virtual, will be virtual, and it's not inverted, it's not ulta, so it will be erect. So the image will be virtual and the image is erect, and the size will always be diminished, small. The size will always be small of the image made by concave lens. Let's just write everything down. So for concave lens and for convex lens, what kind of image is being formed? In case 1, we have the object at infinity. And the image was formed at focus. And this, the convex lens made, in this case, it made real, it made inverted, and it made point size image. In case 2, we brought the object closer to the lens. So it was beyond to f2. The image was between f1 and f2, and the image was again real, the image was inverted, and the image was diminished. Third point, in third case, we brought the object at 2f2. The object is at 2f2. The image was again at 2f2. Very good. Then the image was real, the image was inverted, and the image was of same size. Perfect. Then fourth case, the object is between now f1 and 2f2. Between f1 and 2f1. I made a mistake. This is f1 actually, not f2, f1. This is f1, not f2. f1 is at left hand side, f2 is right hand side, object is our left hand side, the image is at right hand side. So between F1 and 2F2 we have our object. So our image formed will be beyond 2F2 and it will be real, ma'am, it will be inverted, and in this case it will be enlarged. Fifth case, ma'am, fifth case was at F1. Now at F1 the image was at infinity. The image was at infinity and it was extremely large and it was inverted. It was real. Now sixth case always in concave mirror, convex lens. Sixth case was our object was between F1 and optical center and our image was first, the image was virtual, it was not real inverted, it was virtual erect and magnified, or you can say enlarged, magnified, one and same thing. Our object was on the other side of the lens. So it was beyond 2F1. Now it is on the same side. It was on the same side of the lens as that of the object and it was made beyond F1. Okay. Now in case of concave lens we just had two cases. First case, the object was at infinity, the image was formed at focus and the image was virtual erect of point size. In the second case, anywhere on the principal axis, the image was, in this case, in our case we placed our object between, I guess, F1 and 2F1, beyond 2F1 and our image formed was between F1 and 2F1. So in this case we placed beyond 2F1 and the image was then on the same side between F1 and 2F1 and in this case our image was again virtual, erect and diminished. Not point sized but diminished. Our image was diminished. So this is the basic summary of image formation by the lens. These are the kinds of image we see that are being formed from these two lenses. Now moving on to the next. Now we studied sign conventions in mirror, we will study sign conventions in case of lenses. Now for concave lens, let's say what we saw was we had object in here and the image was always virtual erect. So virtual erect, the image was always forming on this side only, left hand side only, correct? So if the image is on left hand side, let's say the basic terminology is left hand side of the O negative, right hand side of the O positive. So the distance of object is left hand side, it's negative, distance of image. Now we just said the image was also made on the left hand side. So when the image is formed on the left hand side, so it will be also taken as negative. In case of this, the image was virtual and erect. The image was virtual and erect. Now focal length, in this case the image is forming on this side, so we'll use the focal length as negative. For concave lens and concave mirror, for both the focal length is negative. Radius of curvature again negative and height of the object above is positive, downwards is negative. In case of convex lens, in this case we use the other side of the focus. The image is forming on the right hand side, so our focus, our distance of image will be on the right hand side, but in case of real and inverted, let's see. Again, left hand side negative, right hand side positive, object is always on left hand side, so object is always on negative. For image, now if you are making real and inverted image
were being made on the right hand side.
This is real and inverted. All the images on the one that were made on the convex lens were being made on the right hand side. So for real and inverted, for right hand side, our distance of image will be positive. For virtual and direct, in that sixth case, the image was made on the left hand side. So for virtual and direct, the image is negative. Again, this, the focal length will use positive. For convex lens, focal length is positive, radius of curvature positive, height of the height above the principal axis positive, downside of the principal axis negative. That's it. That's it. Just like we had mirror formula, in this we have lens formula, but there is just one trick. In that mirror formula, we had 1 by f equals to 1 by v plus, we had plus 1 by u. This is mirror formula. For lens formula, we have 1 by u, instead of plus we have minus. So 1 by f equals to 1 by u minus 1 by v will be our lens formula, which we will use for doing numericals and other magnification stuff. This is f is focal length of the lens, u is distance of object from the optical center, this in this case, and v is the distance of image from the optical center. Next, magnification. If the image is enlarged, it's diminished, it's same size, point size, what will it be? Now again, there is just a trick of sign. In mirror formula, in case of mirror, we had magnification as minus v by u. We had minus v by u. In case of lenses, we will not use minus, it will be just v by u. So we had height of image, height of object, and distance of object from the optical center of the lens. U is the distance of object from optical center of lens. V is the distance of image from the optical center of the lens. Now there comes a really important topic. Now this glass I'm wearing, how do you say what number of lens are you wearing? So I'll tell you minus 2, I'll tell you plus 2, I'll tell you minus half, plus half, correct? How do we calculate that power? That is nothing but it depends on the focal length of the lenses that are used in this spectacle. In my spectacle, I've used these lenses. These are the same lenses we studied. So it is nothing but power of the lens depends on the focal length of this particular lens. So if you need to wear a contact lens, before that someone needs to calculate the focal length of this lens and match it with the focal length of and adjust it according to the focal length of your lens, of the defects that your lens has faced. Now how do we calculate this power? Just nothing. Power is basically the ability of a lens to converge or diverge the light rays. Convex lens was doing what? It was converging the light rays. Concave lens was diverging the light rays. So how much those lens can converge, or if the focus, these are the rays, if this is how they are meeting and if this is how they are meeting, that means their focal length is different. So that is what is called as ability. The ability of the lens to converge the rays in a particular manner is converge or diverge the rays in a particular manner is called power of the lens. Again, the degree of convergence. If the converging, we called it convergence, diverging, divergence. The degree of convergence or divergence of light rays achieved by a lens expressed in terms of power. So power is nothing but 1 upon focal length. If I say my the focal length of my lens is 2, so the power is 1 by 2. If the focal length is half, the power is 2. That is it. That is it. So the power of a lens is defined as the reciprocal of its focal length, and it has a unit. It is called diopter. And now, what was the focal length of a concave lens? What was the focal length of a concave lens? Concave lens, the focal length was negative. So if I say 1 by negative, this is power, so power will also be negative. So the power of concave lens is what? Negative. In case of convex lens, what was it? In case of convex lens, the focal length was negative. The focal length we took was for convex lens. We make both the images, but basically in case of lenses we just assume that light is coming from infinity in most cases. So the power of the focal length of our convex lens is always positive. For convex lens is always positive. Correct? That is it for this chapter. We have completed a very important chapter of class 10th, which is light. We studied reflection, we studied what light is, we studied reflection, different laws of image formation, laws of refraction, laws of image formation. Then we formed the image, we learned some rules how to form that image, and then we used to form the image at different distances from our mirror, from concave mirror, convex mirror. Then we came to on the topic of refraction. We learned what refraction is, how it plays tricks on our mind, how now you know that the head of the person is not displaced actually. He is not a magician, he's just a trick master. So we studied refraction, laws of refraction, laws of image formation from refraction. Then we studied the image is formed. We studied the refraction from the glass slab first. Then we came to the lens. We studied how the refraction helps us form this, helps us converge or diverge the rays using a lens. We studied convex lens, we studied concave lens, then we used sign conventions, mirror formula, lens formula, magnification of a mirror, magnification of a lens, power of a lens, very important topic, and hence it is completed. Thank you very much for joining this session, and will do a lot of numericals in the next video, so follow along. Thank you so much. Learn well, be motivated, be interested for physics. Physics is such a lovely subject that you will fall in love with, and follow us for more of these contents and you will score very good in your boards. I can guarantee you. Bye.